Hello, Anjali. Am I audible to you? So, where are you from? You have not joined last class or you were there? So, you were in the, you have, when I was solving assignment number, this week 0 assignment, you were there. Okay, no problem. So, my screen is visible to you? Okay, okay, no problem, no problem. Not, no need to afraid from me. I'm just asking. So, are you able to see my slides? Okay, okay. So, just tell me where are you from and what are you pursuing actually? That is the okay. Okay, okay. So masters first year, second year. Okay, second year. So have you done this this basics of fluorescence, or have you know anything about absorption emission, or this is the first time you are learning? This is the first time you are learning this course. Not this course, just you know the little bit brief about absorption and emission. Okay, okay, no problem, no problem. And what about Supriya? So what are you doing? Like, okay, okay, okay. So what are you pursuing? Okay, I mean you are pursuing BS, MS or bachelor's. Which course you are pursuing? Okay, you are masters of chemistry. Okay, 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 no problem. Oh, and what about Abhigana Vini? So what are you pursuing? Which program? Okay, uh, person is not replying. Anyway, no problem. So, okay, let's. I hope you have watched Sir's lecture. I think I need to stop my. Hmm, now it is fine. So, I hope you have watched the first week lectures of this course. So, I am PhD student, fifth year PhD student, PMRF fellow, and I am working under the guidance of Professor Pratik Sen, who is the instructor of this course, Basics of Fluorescence Spectroscopy. So today is our second session live, and I will be going to solve question of assignment week and assignment week of this year and the previous year. And if time permits, I will solve assignment 2 and so on. So how many of you have solved this question? A solution has a molar extension coefficient, value is given, concentration value is given, path length is given, what is the adsorbance? How many of you know this formula? Previous class? Okay, okay. So you know this one? Yes. No, no, tell me. You have submitted. Okay. So, okay. So, anyway, if you have submitted, then okay, which means the deadline of the second assignment is already gone. Okay. So, anyway, so I think you have submitted this assignment, and this Anjali and other people have also submitted or not? Anyway, if you not submitted, then no problem. So I hope you know this formula: A equal to epsilon CL equal to log I0 by I. So this is your absorbance or OD, optical density. So according to this, uh, okay, so they are asking for the absorbance. So we have to put what is the epsilon? Epsilon is given 1.2 10 to the power 4 mole minus 1 centimeter minus 1. Then what is the concentration? I'm solving because you have to understand, because calculation is not the problem. In path length is 1. This is in centimeter. So centimeter, mole per. So unit of the what will be the unit of the absorbance? Any one of you. Unitless, yes. So 1.2 10 to the power plus 4 minus 5 into 2. Okay. In the last class I have shown my data, actual PhD data of this absorbance. If you have missed it, just go to my website, this YouTube lecture of assignment, lecture number 1 of this course. You will find it, or you go to the PDF where where I have submitted this, not submitted, I have uploaded on the drive. So weekly log sheet, I think they have already provided you, so you can just log in there. I just click there, you will be able to access. So in that you can see the actual adjustment data of um, my sample. So this is my actual data of my protein I have labeled with some fluorescent dye. Okay, so I think this is fine, both of you. I think four of you, Shivam, Patlika also. Okay, yeah. Okay, so moving on to this, the absorption cross section sigma is related to the molar extension coefficient epsilon by this formula. I think in the assignment this is plus 3, if you have noticed. In the assignment it was wrong, I think. So actually this is the correct. This should be the minus. This is the formula. So just simply value is given, epsilon is given, and the order of the magnitude of this. So we have to calculate sigma square. So sigma equal to 2.303 into epsilon. and epsilon is 10 to the power 4 mole minus 1 centimeter minus 1 divided by Na. Na you know 6.022 10 to the power 23 into 10 to the power minus 3. So just calculate, it is 2.3 10 to the power 4. This is per mole. Na is this is per mole. So unit will be centimeter square after that. Divided by 6.022 10 to the power. This is become 20. Now this 20 will go up 10 to the power 4 minus this. It will be 10 to the power minus 16. So answer is B. In unit you can calculate it out by how this centimeter. Is it fine to you, Supriya Mandal? Hmm. Okay, okay. Question was, the equation was wrong actually. So, hmm so answer is B. So could you just take your pen and paper and try to find out the this unit of sigma, which is centimeter square. Everything is written there. Just try it out. I'm giving you 2-3 minutes. Okay, so with you, I'm also solving. So I have solved till here. So are you able to follow in the box? Okay, Patlika got it. Okay, Shivam is also with us. Supriya, so did you get the centimeter and square? So till here I have solved here. So now my unit here is sigma equal to liter centimeter inverse. Now we know 1 meter cube equal to 1000 liter and 1 centimeter equal to 1 meter equal to 100 centimeter. So just convert this meter cube to centimeter cube. So what will be 100? I should take another page. So 1 meter cube equal to 1000 liter. 1 meter equal to 1000, not 1100 centimeter. So 1 this 1 meter cube equal to cube and cube. Let's put it there. 10 to the power 6 centimeter cube equal to 1000 liter. So 1000 centimeter cube equal to 1 liter. Just put it there. Leave the number. So it will be centimeter cube and centimeter minus 1. So it will be centimeter square. Right? I think it is okay. Now coming back to this question. The molecular cross section of a molecule is this. Molecular cross section, and its absorption cross section for a specific transition is this. So let's say molecule is this big molecule. So cross section of this is this, but the specific transition is this absorption cross section. So let's say only this part of the molecule is absorbing, only this part. So this is your absorption cross section. This is 1 into 10 to the power minus 15 centimeter square. This one is 2 into 10 to the power minus 18 centimeter square. What fraction of incident photons are absorbed? So fraction, this is simple, no? Just the ratio of this portion to the overall. Like 2 into 10 to the power minus 18 centimeter square divided by the full absorption cross section, the molecular cross section. Plus 3, 2 into 10 to the power minus plus 3. This will be the ratio only. Is it fine, Supriya? Okay, this is simple. Moving on to new. Okay, see, this is how it looks like actually. This is the molecular cross section is the full molecule. This is the HNO4 molecule. So this is the molecular cross section. Full molecule. Let's say this is planar molecule. You just this, bisect the molecule, then whatever the area is covered by the molecule is your molecular cross section, and only this part is absorbing, because you are giving that particular amount, the particular wavelength which the OH bond can absorb. So that is why this is the absorption cross section. Of course, this it will be smaller than the molecular cross section. Okay. So, what was the question? Which statement correctly distinguishes molecular cross section from absorption cross section? Okay, out of these two, answer is written there, but any one of you can explain it to me. Okay, so Anjali again she came left. Anyway, no problem. Okay, what did you understand, Supriyo? Tell me. Yes, but the question is which statement correctly distinguish? Distinguish means differentiate. So which statement correctly differentiate molecular cross section from absorption cross section? Which means there should be one property out of these four options which can distinguish absorption cross section from molecular cross section. So if both are representing the same physical area, which means this physical, yeah, this physical area, yes, correct. So this property is not differentiable between these two, right? Yes, yes, yes. And what about, this is, let's say here it is one molecule only. Let's say I have given example of this molecule. Any molecule you can take. You've said normally absorption cross section is always larger. It is not normally, it is always, because molecule is big, only the certain part of that is absorbing, because you are giving that particular amount of the energy. So it is always the absorption cross section is smaller, than the molecular cross section, because molecular cross section is what? Yes, area of the whole molecule. So area of the whole molecule will not going to absorb, means all the bond, all the molecule between the bond between the atoms will not going to absorb, because you are giving particular wavelength. Let's say what I'm trying to say. Let's say okay. Don't go by the stereochemistry of this. Just tell me. No, 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 this is not right. Let me. Mm, okay. first tell me what is this molecule? Do you know the name of this molecule? That's not a problem if you, yes, it is glycerol, yes. So no problem. So I mean to say, let's say it is absorbing at a particular wavelength, OH. Even though this molecule and this molecule both are same in that sense, if we give that amount of energy where the OH bond can absorb, then what will be the absorption cross section for this molecule, glycerol? Only this part, and this part. But molecular cross section will always be this. Oh, this, right? Whatever I have painted in blue color, it is molecular cross section. And OH bond, these are the absorption cross section. So absorption cross section will always be lesser than the molecular cross section. Okay. So option A is wrong, B is also wrong. And what about D? Molecular cross section depend on excitation frequency. What do you have to say about this statement? Molecular cross. Yes, you are correct in that sense, because let's say if it has OH bond and another some bond or something is there which can absorb at that particular wavelength, and that another bond between two atom in a molecule can absorb another frequency. But molecular cross section, here it is written molecular cross section depend on excitation frequency. But molecular cross section doesn't depend on any frequency. It is molecular cross section. Just you have to just bisect the molecule. That is the molecular cross section. Right now, whatever I have this painted in blue, this is your absorption. This molecular cross section. This full molecule, this full molecule are just cut it like the bisected it. It doesn't depend on the excitation or any frequency. It's just the area, kind of. Right. So this is also wrong. What about C? Absorption cross section depend on the wavelength of the incident light. Yes. Whatever you were saying, that the other the like the molecule can have other atoms and other bonds. They can also absorb. So obviously the incident light of the wavelength can also can like this absorption cross section depend on this, because which light you are giving, or I would say like which bond you are exciting, that depends on the wavelength of the light. So that will be the absorption cross section area for that particular wavelength. Is it okay? I mean, understandable to you? Not then little bit explain it more. Okay, so Priya is saying okay, done. Okay, okay, everybody is saying okay, okay, okay. Next question. If absorbance at wavelength lambda 1 is 1.2, lambda 2 is 0.3. So the path length is L1 is equal to L2. Concentration C1 equal to C2. It is given. The ratio of the molar extension coefficient is, okay, this is simple. Epsilon equal A equal to epsilon Cl divided by epsilon equal to epsilon Cl. They are asking for the ratio of the molar extension coefficient. The absorbance is already given. So this is OD. OD at this wavelength. OD at this wavelength. 1.2 divided by 0.3 epsilon, let's say 1, epsilon 2, and this Cl 1, 1, 1, 1, this is 2, 2, 2, 2, 2, 1. So these are same. C1 equal to C2, L1 equal to L2. This ratio you will get. What is the ratio? I think it is 4. Fine, right? This is simple. Yeah, yes, okay, everybody got it. Moving to new question. Okay, the most intense bibronic transition in an absorption spectrum correspond to this. You have to tell me what is the principle behind it. Why this question is coming? What is, yes. Yes. What is the approximation of the Frank-Condon principle? Okay. First, tell me what is Frank-Condon principle. Let's discuss because I want this class to be interactive so that you can understand because the class is already uploaded by instructor, so you can any day you can watch any class. There is no problem. But this is the time for you to actually understand the things by the asking me or this kind of in person. Of course, it is not in person; it is online. But assume that it is in person, so it is like good time for you to like talk to me and clear your doubts. So I want you to be everybody who is there like interactive so that you will be able to understand. That is the main goal of this full NPTEL thing. Just for the certificate anyway you will get it. So there is no problem. So okay, anyway, depends on your requirement. Tell me, what is the principle behind this? What does this Frank Condon say? Nuclear vibration or the nuclear position? Nuclear position. It is like you are giving, this is the molecule, you are giving that particle, this is the energy gap. Let's say this is S0, this is S1, this is particle amount of gap between these two, delta E equal to H nu. This is it, right? So that frequency you are giving here. So this molecule will go to the excited state. here. So that electron, anyway, we always say that electron molecule is going to the higher excited state. Molecule is going. Actually, molecule is not going to the excited state. The electron actually going to the excited state. In the last class, I have told you, like, assume like atom. This is your nucleus. Proton and neutron is present. One cell, two cell. Let's see here, one electron is present. I'm just giving you some example. Let's say this S0, and the particular amount of energy you have given, this electron is going from here to here, this point. This is your S1. This is this representation. This represent only this. That's it. These two are equal. So molecule is not going to the excited state. Electron is going to the excited state. Anyway, so electronic is this electronic transition. Frank Condon says that electronic transition is too fast, and it is way faster than the way faster than the nuclear can change its position. Okay, tell me, uh, why they consider, why they not consider, why do they care about the nuclear position? First, tell me this. Okay, what is nucleus here? Let's just atom. Let's consider this atom. This is the atom. Let's say atom is okay. Let's say I'm giving energy some this as this electron is going S0 to S1. This is your nucleus here. Why they bother about the nuclear position? Vibration. Uh-huh. How? I mean, so what? They will change. They will change, no problem. Okay, tell me for one thing also. Whatever this graph is there, no? This graph. What is the y-axis? Energy, yes. This is energy, right? Perfect. What is x-axis? Position. Yes, yes. Perfect. Position of the nucleus. ठीक है? Now, first, let's say we are discussing. If you have not understood, after the discussion, you can uh, come in the next class, ask question also. But I am going to tell you now and ask question to you also. That's why we will have this conversation. Anyway, if Frank Condon considers that the nuclear position of the molecule or atom will not going to change upon the excitation of the electron, then why there is a difference between this why this difference is there? No. Have you read the Casa's have you read the Casa's rule? Okay. So tell me how the emission, like in this graph, what is absorption? Which lines, which line out of these two represent the absorption and which line represent the emission? Tell me. Yes. Okay. So I'm countering your argument. That is why I'm asking you. Okay. This is you are telling emission, and I'm also fully agree with you. This is emission. But you have said if the nuclear position will not going to change, then what will happen? You are saying the emission and absorption will be same. The wavelength will be same. Something like that you have said. Then tell me why this purple line starting from V dash dash 0 from here, and going here at V prime 6 excited state of vibronic sixth state sixth vibronic state of excited state, and then okay, then emission emission is coming from only from this first vibronic state of excited state to the ground state of any vibranic. Let's say here it's vibronic state, second vibronic state of ground state. Why there is a gap? This gap from this point till this point. Mm, say it again. Say it again. Mhm, mhm. Perfect. You are whatever you are saying is perfect. Perfectly fine. But let's say shift this molecule, this excited state here. Let's say I'm drawing this. One is here, another is just perfectly up. So this is same. Then also situation will be like same. We are exciting from this point, going here. Then this from this point it will relax till here. Emission will come from here till here. Did you get it? So yeah. So your first statement that the excitation, the absorption and the emission will be same at the same wavelength. Probably it is not correct then. Yes or no? Yes, no? Yes, yeah. So your statement is wrong because the wavelength will be changed. Tell me, what is this gap? There is a specific name of this gap. Yes, it is vibrational relaxation. And one interesting thing I'm also thinking right now. Mm-hmm. Okay. Take this energy also from here V double prime to V double prime 0. Yes, this energy. I'm saying this is X, this is Y, this is Y. Tell me what. Uh, I know what you are trying to say. You are trying to say that when we excite the electron, it will go to the Brownian state where the maximum overlap of the wave function will be there. Probably. Yes, probably. Perfect. 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 So that will be the most. Yes. So that wavelength where these wave function will overlap to each other will be the highest, most intense peak that we, yes, that we call the maxima, absorption maxima or emission maxima. So, so it is like if this is your absorption, this is OD, this is wavelength, right? So this place, this wavelength, this wavelength, this particular wavelength, at this particular wavelength, the absorption is most intense because the overlap of the wave function is higher, right? That is what you are trying to say. Okay, so my question is that you have said that this is vibrational relaxation, this gap, X gap. Now tell me, this X gap, this X gap plus Y, this Y, here to here, what it called, what it will give you, what is the name? Radiation length transition. But let's say if you have, if I'm giving you absorption, um, absorption spectrum and the emission spectrum, so the energy, there will be energy difference between these two, right? Because why I am saying, why I am telling you this, because you have said if the nuclear position will be same, the absorption wavelength and maxima will be same, emission maxima and absorption maxima will be same, but this is not the case. So energy difference is there. How much? X and Y. Total energy difference between absorption maximum and emission maximum. What does it call? Have you heard about Stokes shift? Yes. Patlika said Stokes shift. Yes, it is Stokes shift. Maybe it is hard to visualize, but I will show you. Let me take another slide. Then see. This is, let's say, wavelength. This is intensity. So let's consider this as a green. This is green. Green is emission, absorption. So I have indicated correctly or not? Just tell me that first of all, or it will be, or I have indicated opposite. So absorption, whatever I have said, that the absorption is first one, emission is second one. So you are also agreeing with this. Yes, perfect. So the difference between this is your, this is your, yes, absorption maxima. This is your, yes, emission maxima. The difference between these two, this difference is called Stokes shift. This is Stokes shift. So the difference between the maxima is called Stokes shift. So here, whatever you are this purple graph here, purple arrow you are showing, this is the maximum intensity you are observing here, because the maximum overlap, probability of overlap between the two wave function is higher here. So I am considering this is the maxima, and for green one, this is also the probability of overlap between the two wave function is higher. So that is I am considering uh, um, the maxima of emission. So what will be the gap, energy difference? This x from here to here and from here to here, this and this, x and y. So total difference between the emission maxima to emission min absorption maxima to emission maxima will be this, right? So this will be, it should be energy difference between x plus y. This should be x plus y. So this is called the Stokes shift. So the first statement you have made, that these two will come at the same place. If the nuclear position will be same, it is totally wrong, right? Now I don't want to prove you wrong. I just want to tell you something. That's it. So okay. So back to my question. Coming back to my question, why this gap is there? If the Frank quantum considers that the nuclear position is not changing, but this is the no position of the axis is the position of nucleus. It is changing, and they have considered according to their principle Frank quantum that the nuclear position is not changing, right? This is the basic principle that the electron transition is higher, much faster than the nuclear, so that the nuclear position cannot be shift, cannot move. Tell me why this is there. Tell me. This should be like this case. Did you get my question? First of all, tell me. Yes, no, anything? Okay, you are not responding. Probably you are not getting the question. I believe so. Okay, I believe so. So first of all, Okay, one more question. One more question. Are you there? Are you getting bored or what? You're not replying, that's why I'm asking. No, no, Patlika is there. Okay. Uh-huh. Yeah. So if you got my question, then there should be some problem, right? There should be some problem. No, 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 no. According to the principle, they always okay. Anyway, first tell me why they have considered this. The electronic transition is way faster. The nucleus cannot move. Can you can you tell me somehow how you can why they are able to actually um as- but okay. Patlika is saying mass of nucleus is higher than the electronic mass. Hence, the nucleus moves slower compared to electron. Yes. So this is the answer of my last question. This is the answer of my last question. So what is the let's say here in this what is the nucleus? Nucleus is made of proton and neutron. So let's say one proton is there. I'm considering the hydrogen, right? So what is the mass of the proton? Tell me what is the mass of the proton? Mass of mass. That's it. That's it. Whatever I wanted to tell you, you have told it. You have just told me that it is 2000 times higher than the electron. So that is why they have approximated that it is the mass is so heavier. It is heavier than around 2000 times or 1000 times, so that it cannot move that fast at which the your electron is moving. That is why they have approximated this. Okay. Anyway, a lot of information, lot of Frank Condon insights I have given you. So let me give you an answer of this question. Why they have given this? Why they always show this? Position of the nucleus is different. I mean, it is shifted, not different. It is shifted little bit toward righter side. Okay. Okay. I can I ask you one more question? Is it possible that this can go to the left side in any case, in any way? Sure. How so? No, my question is that what do you understand by these two? This potential and this potential. These are two potential of what? Two different molecule? Same molecule? Same molecule. Exactly. So I'm saying that this potential, this potential can be shifted like here, like here, something like this. So the nuclear position will be here then. So that x-axis is what? Position of the nucleus. It is not the vibration. Position of the nucleus. It is the position, not the vibration. Anyway, this you have to find it out. Come back in the next class. Okay? You will be surprised. Not be surprised. You will learn something. This question will teach you something. Anyway, if you have time, you can come tomorrow, like in the next class. Anyway, we have discussed a lot about this. Let's come back to the question. The most intense vibronic transition in absorption spectrum correspond to. This we have discussed. The option C, maximum overlap of vibrational wave functions. Okay, let's move to high energy transition, maximum vibrational excitation, lowest absorption cross section. This is not correct. And one more thing about this question: why the excited? Why this change is there in the nuclear position? Because even though they are considering, according to the Frank Condon, the Born-Oppenheimer approximation is there. They are considering that the nuclear position is not changing, but when you excite the electron, the nuclear position, because now the electron from S0 to S1 is going, so the charge of the nucleus and the electron will be spread out. So the position of the nucleus will change. Actually, it will change. So for the calculation, they have approximated like that the position of the nucleus is not changing, but it changes. Otherwise, the calculation will be very difficult. So they have separated out the nuclear part. If you read about the Born-Oppenheimer approximation, then you will understand. Because in that, we have considered that the position of the nucleus is not changing. If we consider the position of the nucleus is also changing with the electronic transition, then the calculation will be very much difficult. That is why they have considered in this Frank-Condon principle that the position of the nucleus is not changing, but it changes. That is why they have always this change is there. This not drawing the potential just one above the, like both of them are not above to each other. That is why the nuclear position is different. Read about the Born-Oppenheimer approximation. Okay, fine. I think I have given you the answer. Nice. Okay. Moving to next question. This is the opaque blocked section in the rotating optical system is mainly used to. So have you read the such lecture? This NPTEL lecture, video lecture. Okay, so you must have seen this absorption spectrophotometer instrumentation. So this basically what does it do? When both are opaque, so sir is actually very nicely explained that when one this transparent, this is this is transparent. So what will happen? This light will go here, this side, then it will reflect. Then if it should be in that case, your disk will be mirror. So okay, this is mirror for the first one, which means it will be reflected, transferred for the second one, then it will detect your okay, this is your sample. I0 will be here, I will be here. This I'm not going to tell you, but an opaque will match with the opaque one. Okay, fine. So basically, this opaque are present in this rotating disk because of the thermal to actually eliminate the thermal noise or the dark count, I would say, of the detector. So that is why when both of them are opaque, still a detector will detect some count. It will give you some absorption. Let's say this is for absorption spectrophotometer. Photometer. So detector like PMT detector or any other detector. So these are detector will have the thermal noise. So electron will always ejecting. So to eject, to eliminate this dark count. So why dark? Because at that present of that point, the light is not passing. That is why still you are getting that count. That is why it is dark count. So to eliminate that, we use the opaque section of the rotating optical system in this absorption spectrophotometer. Okay, so option is C is correct, but as I have discussed little bit about the thermal noise and this thermal noise of the detector. So, do you know anything about the detector thermal noise? Anything? Perfect, perfect. But my question is that why this thermal noise or dark count is coming? If light is not passing, then there should not be any count in the detector. The count in the detector means you are seeing the absorption. Let's say for absorption case, for absorption instrument, you are seeing some kind of spectra, but it should be zero if light is not passing. So why this is case? Why it is the case? Have you read about detectors? Anything about detectors? PMT detector, and I guess you have not read it, so no problem. I'm giving you assignment. You can read it. PMT detector and you know Albert Einstein. You have to. So everybody knows. So tell me if you know Albert Einstein. He, yes, perfect, perfect, perfect. So this PMT work on this photoelectric effect principle. So you can read it out. This much you got. Then you will understand why this thermal noise, even the light is not present, is still electrons are ejecting. What does this photoelectric effect tell? Let's say this is the metal surface, photon is coming. If your threshold energy higher than the threshold energy, the electron will eject, right? That is the photoelectric effect. But in this case, in the PMT detector, light is not coming. Still the electron is ejecting, and that is why you are getting the count. And in the absorption spectrum photometer, you are getting this some kind of absorption without giving the light. So my question is, why? Why this dark count is coming? This you will find it out and come back in the next class. This is your assignment. Anyway, 7 question. Let's move to next question. Why does a simple double beam setup using two separate detectors still suffer from measurement errors? This I think you have told me just. Yes. This you have told me. That detector have different spectral responses. So that is why this setup came. This only one detector is there, but the disk is there. It is not changing. Because if both the detectors, let's say this detector and this detector, even if you are splitting this light in 50-50, 50% going here, 50% is going here into this direct detector, into this detector. But both the detector are, but their response is same. They are detecting, like their efficiency of detecting the photons is different. Then there is no point of reference. This I0. Let's say this is bad detector. I'm saying this is bad detector, and this one is good. Good bad means this response is good, response is bad. So anyway, I0 will be less because it is not counting your, even the light is coming, it is not counting. So whatever your the absorption you will calculate, absorption equal to log I0 by I. Here is different, here is different, so this always be wrong. That is why. And take my word for granted, no two detectors in the world are identical and have same response. That is why this problem is here. That is why this system is modern system we are using. Fine. Okay. I think till here everybody is fine. Let's move to next question. Is it fine, right? Or should I? Okay, okay, fine. Okay. Negative solvatochroism occurs when? Okay, what do you mean by solvatochroism? Just this sentence, this word. Polarity, yes. Polarity of what? Nope. Polarity of the solvent. What does this mean? Chromism. Colors. Yep, yep. Yes. Okay. So negative solvent chromism occurs when negative, positive is just the terminology. You have to understand the concept. Then you will figure it out. No problem. It simply means that let's say this is the ground state. This is excited state. If it has the higher polarity, and if you are giving this is the condition. Okay. So let's say this this here molecule is in polarity P1 in a solvent. I am assuming X solvent. Name of the solvent is X. Of the solvent polarity is P1. In this case, the same molecule. Let's say molecule was A. The same A molecule was here. Same molecule is A is here in the different solvent. And this solvent is, I am saying this is Y. Y. Polarity of this Y molecule, Y solvent is P. And the condition is that the polarity of the P2 is higher. So what will happen? If the ground state polarity of the molecule of A is higher, then sir has actually explained very nicely that the polarity of the P2 is higher. Here the 4 number of ions will come here and stabilize it, because positive negative it will anyway stabilize. But in this case, P1 molecule, P1 solvent, the polarity is less, so it will not stabilize that much compared to P2, because only 2 negative, 2 positive will be there. So condition what will be like? Condition will be, this is ground state, excited state. In this case, when the polarity is higher, what will happen? This Z2 will be more stabilized. So this difference is there. Stabilized means the energy is less. So that is why the band is lower than the G1, and it is much lower than compared to this band. See, E2. Okay, he left. Anyway, compared to this, it is less. Why? Because the polarity of this is polarity of excited state. Dipole moment of the excited state is lower than the ground state. So that is why it will stabilize very less compared to this. So then the energy difference between this energy difference is lower than this. So energy difference lower means if you take the emission, what will happen? It will go to the negative side. Negative side means blue shifted. Means in this case, if the emission is here, in this case emission will be like this. It will shift to this side. This is the full negative solvator explanation. So this is your negative solvator negative or blue shift. So the answer of this is ground state dipole moment is larger than the excited state dipole moment, B. Solvator can be explained considering the solute as an electric dipole. In molecules exhibiting negative solvator equilibrium, the dipole moment of the excited state is generally lower than that of the ground state. Okay, I think you have probably got it. What if you not, just tell me. But okay, okay, and tell me what is positive solvator equilibrium? What will be the conditions? Just this much only. Yes, it will be red shifted. And what will be the condition has to be there to uh, get the red shift? P2 solvent. P2 solvent. Uh-huh. So to get the, I think you got the concept, but you are missing one point. If to get the positive or red shift, positive solvatism or red shift, the dipole moment of the excited state should be exactly should be higher. Then what will happen? See this, this, this. This is Z1. This is E1. So the dipole moment of the excited state is higher. Then what will happen? In the case of the high polar solvent P2, it will stabilize more compared to this. So difference between this, this is difference is less. This difference is high, and so this difference is high. This difference will be low. So what will happen? Let's say your emission was here in this case, but in this case, what will happen? This is your wavelength, lambda. It will, yes. Condition, this is in P2 polarity, and mu E is greater than mu C. This has to be the condition to get the red shift in the higher high polarity solvent. Okay, everybody is with me. Shivam, Najma Banu, Patlika is there, yeah. She's celebrating. Okay. So can I move? Yeah, yeah. Okay. So what is the purpose of grating in the monochromator of a spectrophotometer? Uh, okay, I think you have not seen by your mm, physically seen the grating. So do you know how does the grating look like, or what does that mean? So I can tell you anyway. it is like something like this. When light is falling here, it will, what it will do? It will disperse the light. Let's say white light is coming just like the prism. Have you seen this? Prism. White light is there. Let's say this is here or here. You have 7 lines, something like this. Full rainbow. Just like the prism. So this grating also separates the light. So let's say this is your source, white light, or your tungsten lamp in your spectrophotometer. This is after hitting to the mirror, it will going to the grating, and this grating will disperse the lights into whatever wavelength, whatever uh, in all the wavelengths. And after hitting this, then after from the grating hitting this mirror, it will go to the detector. So here we have pinhole, this pinhole in the detector. This detector will then, according to the pinhole, or this pinhole means what? During the during your taking the data, yes, it can select only whatever wavelength you will provide. Let's say 1 or 2 nanometer wavelength. That it will scan at one point of time only. Let's say 1 nanometer wavelength, and it is keep on scanning from, let's say you are given from 200 to 700 nanometer. Near game, you want to get the absorption from this to this wavelength. So at one point of time, it will scanning 200 nanometer. Then again, another second, 201, 202, like that only. Let's say this pinhole is there, but this, let's say mirror is changing or disk is changing. This is the instrumentation part. So that is only there, only one light. So that is why this is important. Otherwise, the full, otherwise it is very difficult. So in this here, that is why we are giving you this, by drawing this bulb, tungsten bulb. It is just giving all kind of lights, constitute of, made up of all the different lights, and it will have all the components of these lights from 200 nanometer to 700 nanometer. So this is the purpose of the grating in the monochromator, that it split the light into its component wavelength. So answer: to split light into its component wavelength. A. To amplify the intensity of the light beam. No. To collimate the beam light. No. It will disperse. To reduce the high order refraction. No. The grating is a crucial part of the monochromator that disperses light into its constituent wavelength through diffraction. This allows the spectrophotometer to isolate and measure the specific wavelength, enhancing resolution and accuracy. Yes, of course. This is for like your absorption from here to here. This is intensity. This is lambda, going here from here to here. If all the light at one time detector is observing, which means you will not going to get this beautiful absorption band, absorption graph spectrum, because the every time, let's say at this point, You're not measuring only this wavelength, all the wavelengths you are measuring. So basically you will get some intensity something like this. Maybe here higher or something like this. Like this. Maybe. I don't know. I'm just giving you some. So that is why it is important to select only particular wavelength. That is why you are getting that is why you are getting this data. Okay, I think it will be fine. Should be, yeah, fine. Okay, moving ahead. So these are the questions from previous year assignment. So among the following, the condition that violates the Lambert's-Weird law is, have you studied or have you read this inner filter effect? Inner filter effect. Anything about inner filter effect? No. Inner filter effect. Okay, inner filter effect means the concentration of the solute of the sample is high. So what is means? Let's say this is your cuvette and this is your light beam, and here is your detector. Detector is here. Detector is here because in emission instrument the detector is always placed 90 degree to the your excitation wavelength. So this is your excitation wavelength. Excitation wavelength. This is the emission here collected at the 90 degree only. So this is 90 degree. Detector is here. What will happen when the let's say concentration is low? Concentration is low. What will happen? This light will go pass till here and also go here. Like it will transmit, and some molecule will absorb the light. So these molecule, what will they will go to excited state and emit. And emission, emission is directionless. Emission is directionless. Yes, emission is directionless, which means this molecule will absorb the light and will emit at any direction. Any direction. Okay, first question to you. Even if you not studied, have you studied emission, this emission spectrophotometer, fluorimeter instrumentation? Not the absorption. Emission. No. So, but in the second week, I think there is a lecture. You should be. Have you seen the second week lecture? Okay, no problem. So, okay, find it out that I'm giving you one question. Why this detector is placed 90 degree to the excitation? Okay. The question is that I can also place emission here, this detector here. Why here? Here also. Because emission is directionless. Right now. Here also. At this position or somewhere. Like this is also 90. This is also fine. Because this 90 is fine. So why not here? Because emission is everywhere. Like directionless. So even if you are collecting at 90 degree or 45 degree, 75 degree, or just here 0 degree, no problem. Even if you have not studied, just think about it. Why? But in the emission, we are not determining the transmission of the light. For transmission of the light, we are using the absorption spectrophotometer. This is the emission photometer. We are just There are two instruments, absorption and emission instrument. So here we are observing only the emission, this part. Mm, the purple, not the purple, green, this light. Any wild guesses? Okay. So it is at 90 degree because when you place that here at this position, you will detect the transmitted light also with the emission, because all the light you are giving for the excitation will not going to absorb by your sample. So the transmitted light will also be collected by this detector with your emission. So you will not, yes, so you will not be able to differentiate, or I would say you'll get the wrong emission data. So that is why actually both will be together. You'll because the light is, yes. So maybe it will be like I have given you this shown you this is, let's say, absorption, this is emission, this is absorption, this is emission. So maybe after the absorption, after let's say that if the detector is at this place, maybe you will get spectra something like, because molecule have absorbed the wavelength, this light, but the transmitted light will be there. So the intensity might decrease from this, will be something like this, and the emission will be like this. After placing this detector here, you'll get something like this. Maybe your alone and your absorption previously. If you take the absorption, if you take this qubit in the absorption spectrophotometer, you'll get the absorption something like this. And this point is critical. These are overlapped, sometimes very overlapped. These are the stroke shift which I have talked about in one of the question is not high for all the molecules, all the systems. So it will be difficult to differentiate. Maybe it will look like this, emission something like this. This also can be true. So this is coming because of the absorption. If you place detector here, I think you got the point. So to avoid that, we are placing the detector at 90 degree. You'll get the clean emission data. No contribution of the transmitted light. That's it. Okay, this is about the detector. Now, what about the concentration? Now here the sample was dilute. Let's say same qubit. Now the sample is detector is here D. Now I have prepared the solution, high concentrated solution. extremely high. And and this is your excitation light. This is your tungsten bulb. This is glowing. Let's say light is going here. Excitation. Now tell me what will happen. Perfect. Yes. Yes. Okay. You are okay. Uh-huh. Your first reasoning was correct that the detector will not going to detect the emission that prominently. Why? Because when if you have like whenever you will work or maybe you have worked in a spectrophotometer or fluorimeter in any of the instrument, there is called the pinhole in the the how much wavelength you want to select. It's 2 nanometer, 3 nanometer for your absorption or emission. The bandwidth, we call it bandwidth. So let's say only let's say 2 nanometers. So the pinhole is there only whenever we excite the lamp, we excite the sample. Only this part, only this part. I should take another. Only this green part. I think you are able to see. Yes, only this green part at the place at the position of green of the molecule, they are going to only get excited and their emission will be going to detected by the detector. So in the high concentrated sample, what will happen? This light, this light will not reach till this green. It will absorb by these molecule here only. But pinhole was here, so emission will be here, here. It will not reach to the detector. So that is why this Lambert-Weir's law will fail. Okay, this is the okay. Lambert-Weir law in the case of the absorption. Okay, I've told you in the case of the emission only. Emission. So Lambert-Weir law is okay. Epsilon Cl. Even though if you consider Lambert-Weir law means this is absorbance, means spectrophotometer, not the fluorimeter. So I am telling you about the fluorimeter. So anyway, just remove this. I can tell you this is the detector D. Again the transmitted light. The light will not be transmitted because all the molecules have been absorbed. Okay. So detector will not going to detect the transmitted light, and you know the this absorption log I by I zero. I zero is this. I is this. If you're not going to detect I, so you will not get the absorption. Even though you will get some transmitted light, but the absorption will be distorted. Like according to this formula, what will happen? If you increase the concentration, let's say this is absorption, this is concentration. Tell me how we have to plot the graph, how the graph should look like. Yes. Yes, perfect. It will be like this. and this. So this is the maximum concentration. Till here we can absorb, we can collect the absorption. So this is called the inner filter effect. So this violates this Lambert's-Beer law at the high concentration of the solute. Fine. Because reasoning I have already given you, so no problem. Okay. Can I move to next question? Yes. For a solution with an absorbance of 0.04%, the percentage transmitted light is about, so you know the formula. This I have already calculated here. You can see that epsilon CL equal to log I0 by I, and the transmittance is equal to I0 by I by I0. Then if you convert these two or substitute this here, epsilon minus I0 by minus log T. And percentage of T will be I0 by I. They are asking for the percentage transmitted. Okay, 100. Right. So you can take log of percentage T equal to log 100 plus log I by I0. So this is log means log 10 to the power 2 base 2. So it will give you 2 plus log I by I0. 2. This I by I0 is minus of A. This can also be written as minus log of I by I0. So if you substitute here, only minus A. So the percentage of the formula becomes log percentage of T equal to 2 minus A. And the absorbance you are already given 0.4, which will equal to, absorbance is given. Yeah. So you can calculate. This is simple. Nothing is, you can do the calculation anyway. Next you can figure it out by taking the, this will become 1.6 something. Yes, 1.6, and then 10 to the power 6 something, 1.6. This is in log percentage of T, and it will be, oh, percentage of T equal to 10 to the power 1.6. 1.6 will be more about 40%. Fine. This is just the calculation. Yes. Moving on to next question. The approximate time taken for a molecule to absorb a photon and undergo an electronic transition is. This you must have know this. The molecule Yes, and the calculation is written here. Let's say the way sir has solved that the speed of the light, 3 into 10 to the power 8 meter per second, right? And the size of the, then the, let's say wavelength of the light is 400 nanometer, and we are assuming that the wavelength of the light associated with the size of the photon, which means that the size of the photon means this is the size of the photon. So let's say this is the size of the photon. To cross this point by the light of this size of the photon, basically this has to travel this distance. This is the point, 0 point, and this is the size of the photon. Just like the train, the train is passing at a point, so we have to take the distance of the um, train to calculate the speed and time. So the speed equal to your distance divided by time, and distance here already given 400 nanometer or angstrom divided by your, this is time you have to calculate, the speed is already given. So if you calculate, you will find it out time in femtosecond, 15 seconds. I think clear, right? No? Yes, okay, fine. Okay. The Frank-Condon principle assumes that the electronic transition much faster compared to the nuclear motion for any molecular system. This question we have discussed a lot, right? So no need to explain here. Okay. Which of the following is directly responsible for broadening of absorption band? Broadening of absorption band means, maybe absorption band can be like this. If broadening of absorption means this. The width of the absorption is small here. Width of the absorption in this case is higher. So this is called the broadening of the absorption band. So the question is which of the following, or this is multiple select question, directly responsible for broadening of absorption band. So for nuclear case, for the atomic case, I have already explained like this. If this is the case, only one wave, it will the absorption will come at only one wavelength, right? Because of the sharp, only one transition is there. But when the molecule is there, lot of vibration states are there, rotational states are there, as it is depicted here. These are the vibration states. So all the transitions are possible. Of course, as we have seen in the Frank-Condon principle, in that diagram, the intensity of the transition it will be higher or lower, but the transition will be there. So that is why you will see the broad spectrum. So if you collectively see the spectrum, how it will look like? Something it will look like this. So this is that is why the spectrum with the vibrational structure of a molecule is broadened. Perfect? Okay. So this is fine. This is we have understood. What do you mean by Doppler effect? Doppler effect is that, I think you heard it, right? Before. Okay. So it is like the Doppler broadening due to, yes, yes, yes. That is only because I don't know how to explain it to you, but I mean I know how to explain, but it will be difficult. But if you know, then it will be much easier for me to tell you. So, like the atom of the molecule, if you excite it, it is emitting then or absorbing. These atom or the molecule actually um, absorbing or emitting at different wavelengths. So that is why the broadening is coming. Because the velocity is different. So they are not reaching the detector. Even let's say maybe it's the same wavelength, but yeah, the time taken for the photon is different. Velocity of the uh, same of the photon emitted at a particular wavelength will be different. Then what will happen? Let's say one photon is emitted at 200 nanometer, and that particular photon at 201, 202, or here 198, 199, and all the molecule will be absorbed. Like it will be detected by the detector. That is why if the velocity of the atom or the molecule will be different, or your electron, then the broadening will come. So that is why because of this Doppler broadening, Doppler effect, the broadening comes. So here I have written the Doppler broadening is the broadening of the spectral line due to the Doppler effect caused by the distribution of the velocity or of atom or the molecule, different velocity of emitting or absorbing particle result in a different Doppler shift. The cumulative effect of which is the emission absorption line broadening. This result line profile is known as the Doppler effect. The relative motion between the light absorbing molecule and the observer cause the Doppler broadening. This effect is more prominent in the gas phase where the thermal motion of the molecule affect the observed frequency. In gas phase, it is easier to understand because they are interacting. Let's say this molecule is interacting with this molecule, making some bond, then it will absorb little bit different than its native state, and maybe after at a certain point of time this molecule is making bond with different molecule, so maybe there is a shift in different because of this interaction, the shift in the intensity frequency will be a little bit there. So that is why if your sample is in the gas phase, because of this interaction with other molecules, the absorption or this your broadening will be there. I think I made my point clear probably. And the third one is intermolecular collision. So intermolecular collision in condensed phase, liquid, solid, or high pressure gases. Liquid means liquid. They are like bond with water, like bond with bond, and solid is like it is packed, or high pressure. Frequent intermolecular collision cause pressure broadening. Of course, they will collide. The liquid, solid, and the high pressure gases, they will collide more easily. Like the collision will be higher. So in this case, just whatever I have explained, the bond is making with this, and that. So because of this bond making and breaking, there will be shift in from the native molecule. Let's say this is your native molecule, so it will be difficult. It will be different. So the broadening will come, something like this. I think so. The answer for this question is all of the above. I think I made my point clear. Is it okay? Not okay? Tell me. Patlika is okay. What about Shivam? What about Najma? What was okay? Supriya Mandal is also okay. This I already explained. Okay, what is the purpose of the reference cell in the double? Okay, let's see what is the time. Only allotted, I have been allotted only 2 hours to conduct this session. Okay, it is already 2 hours, so I am stopping here, and next question I'll do in the next class, like other question, in the week assignment of week 2 of previous question. Actually, I wanted to finish this, but anyway, 7, 8, 9, 10, week 2 assignment week 2 I'll come. In the next class I will do, and also these questions, this question and previous year week 2 assignment questions. So in the next class come, I'll solve it. Anyway, I'll solve it. Okay. I'm closing the session here now. Nice to interact with you, and please join in the next session, which will be happen on the same time on Sunday, 4 p.m. to 6 p.m. Okay, I'm closing the session. Bye.